Now that we've got some of the basics of sequences and series out of the way, our next few sections are going to focus on specific tests we can do on a series to determine if it converges or diverges. Some of these tests won't actually give us the sum for the series, but at least it pushes us in the right direction to tell if our series will converge or diverge. So one very important type of series that has its own test is called a geometric series. And we actually saw these in the last couple sections, but I didn't specifically name it. I wanted to wait until we got to this point. So a geometric series is a series of the form we're going to be taking the sum from 0 to infinity of a times r to the n. A cannot be 0, and the r value cannot equal 0 or 1. So a is just a coefficient, and the r to the n is an exponential piece. So we've seen a couple before where we had this exponential relationship between the terms. That n power does not apply to the a, it only applies to the r. R is called the ratio for the series. And if we were to write some of these terms out, one special thing about the geometric series is it starts with n equals 0. And we will have a formula to find the sum of a geometric series, and that specifically requires n to start at 0, even though there's a way around it if n doesn't start at 0. So if we plug n equals 0, any number to the 0 power is just 1. So all we get back there is our coefficient. When n is 1, we have a times r. When n is 2, we have ar squared, ar cubed, and so forth. So from term to term here, we have a common ratio. To get from one term to the next, we're just multiplying by an additional factor of r. So this series converges if the absolute value of r is less than 1. And it's pretty easy to see why. If we have any hopes at all of this sum eventually stopping somewhere, then these terms have to go to 0. So if you think about a number that's less than 1, so like a half, that means every single time I move from one term to the next, I'm multiplying by a half. And multiplying by a half makes the next term smaller than the previous, because I've just taken the previous term and multiplied by a half. So these terms are getting smaller pretty quick when your r value is less than 1. But this series will diverge if the r value is greater than or equal to 1. Now, I had said up here we don't really want r to equal 1, because 1 to any power is always going to be 1. And really all we're going to end up doing is adding a to itself over and over and over again. Since in that case the values never decrease and eventually go to 0, our sum is never going to stop anywhere because we're adding a to itself an infinite number of times. So even though we really don't like r to be equal to 1, that is a case where this series would diverge if we recognize that and saw it happening. If this sequence is convergence, if the series is convergent, then this type of series has a nice little formula that we can calculate to find its sum. And like I said a minute ago, it requires our index to start at 0. So the sum of a times r to the n is always going to be a over 1 minus r. And there is a way to work around if we, for some reason, find a geometric series that doesn't start at 0. Then we would still want to use this formula, but that formula includes every single term starting with the 0 term. So this would be our starting point, and then we would have to subtract off the terms that aren't included. So if it doesn't start at n equals 0, let's say it starts at 2. We can still use our formula because that's going to take care of an infinite number of terms for us. But this formula assumes it starts at 0. So the 0 term is missing and the n equals 1 term is missing. So what we do is we just subtract off the 0 term and the 1 term. I'm going to call them a sub 0 and a sub 1. So we're going to look at a couple of geometric series and determine convergence or divergence. And if it converges, we're going to find the sum. So the first one we have is n equals 0 to infinity of 2 times 1/3 to the n. So we start with a really simple one. They're going to get a bit harder, and usually it's just the algebra, some algebra manipulation that makes them tricky. This is a classic geometric series. I've got a coefficient, and then I have an exponential piece. So here we're dealing with a geometric series with a equals 2 and r equals 1/3. So the absolute value for our r is 1/3, which is less than 1. So it's convergent. And it's as simple as that, just by looking at your r value. So we have absolute values on there because if this was negative 1/3, it would still be convergent. The sum would be different, but the fact of whether it converges or divergent would not change. This one starts at n equals 0, so we could use our simple, just original sum formula to calculate the sum, which is a over 1 minus r. So the a value is 2, and then we've got 1 minus our r value, which is 1/3. So 1 minus 1/3 is 2/3, and then instead of dividing by that 2/3 fraction, I will flip and multiply, and we get 3. The sum of this geometric series is 3. For the next one, we're going to find the sum from 1 to infinity of 4 to the n over 2. This one is set up slightly different, but it is still a geometric series. You're going to want to do some algebra to get it to look like a times r to the n. We want our coefficient to be a factor written in front of the exponential piece. So dividing by 2 is exactly the same as multiplying by 1/2. So that rewritten series means the exact same thing, but it's now in a format that we recognize. So we're dealing with a geometric series that has an a value of 1/2 and an r value of 4. So the absolute value of our r is 4, which is greater than or equal to 1, which means this one is divergent. Convergence and divergence of a geometric series has nothing to do with where your n value starts. The only time we need to consider where the n value is starting is when we go to actually compute the sum. And since in this case the series diverges, that means it does not have a sum. So there's no point in computing the sum on this one. The last one we're going to look at is the sum from 1 to infinity of 5 over -2 to the n. And just like the last one, this one's not really written in a format that we recognize, so we should try to rewrite it so that we can identify the a and the r. We're expecting the piece that's not raised to the n. That's our coefficient. And since that's in the numerator, we could just pull it out. What we're left with is 1 over -2 to the n. And this is exactly the same as saying -1/2 to the n. Because when I raise my fraction to the n power, 1 to any power is still going to be 1. So it doesn't hurt us to go ahead and lump the 1 in with our -2 and raise the whole thing to the n power. We would get the same exact result. And now it's a recognizable format. We've got a geometric series with a equals 5, r equals -1/2. So the absolute value of r is 1/2, which is less than 1, which means this is convergent. And because it's convergent, we can find the sum. So when it comes to finding the sum, this is where we have to pay attention to where our particular series starts at. Our series starts at 1. The a over 1 minus r formula assumes we start at 0. That doesn't mean we can't use it. That just means we're going to have to do this calculation and then exclude the 0 term from our sum. So we said a was 5, r is a -1/2, so this is 5 over 3/2, or 10/3, but this assumed that n starts at 0, and we're missing the 0 term. So we've got to figure out what the 0 term would be for this series, and we need to subtract it off that 10/3. So the 0 term means we're plugging 0 in for n. -2 to the 0 power would be 1. 5 divided by 1 would give us 5. So we don't have the 5 in our sum because we didn't start at 0, so we need to take 5 out of our sum. So this is 10/3 minus 15/3, which is -5/3. So the sum for this particular geometric series, since it is convergent, is going to be -5/3. Another type of series that you may be able to recognize just by looking at it is called a telescoping series. And a telescoping series has a very specific format. The terms in here could be anything, but what's special is you usually have a subtraction where the second term in that expression looks very similar to the first one. It's just what you would get if you went out to the next term in a sub n. And I'll show you some actual examples of what this looks like. But if we generate some terms here, I'll show you the special thing about the telescoping series. If we plug in n equals 1, I get a sub 1 minus a sub 2. If I plug in n equals 2, I get a sub 2 minus a sub 3. If I plug in n equals 3, I get a sub 3 minus a sub 4. And this just keeps going forever. So notice that the second term from each piece is going to end up canceling off with the first term of the next one. So the a sub 2's cancel out because we've got a subtract and an add. The a sub 3's will cancel out because we have a subtract and an add. And this long giant sum is just going to collapse down to be your first term plus the limit as n approaches infinity of your second term. Excuse me, that's not plus. That is going to be minus. So just the very first one and then the very last one, which there technically isn't a very last one, so we have to write it as a limit. So to tell if these things converge, a sub 1 is going to be a definite number. The only thing in question is whether this limit will be a definite number. So if the limit as n approaches infinity for a sub n plus 1 converges, if that limit converges, that means we're able to find a finite number answer for that limit. And then if that's true, we'll be able to do that subtraction and get a finite answer. So if that limit converges, then our series is going to converge. And the sum is going to be that expression I just wrote above. A sub 1 minus the limit as n approaches infinity, a sub n plus 1. So we just need to see where those terms are going. If those terms are eventually going to reach a finite value, or if they're just going to blow up to infinity. So let me show you a couple of examples of telescoping series. For the first one, we're going to have the sum from 1 to infinity of 1 over n minus 1 over n plus 1. This is a classic telescoping series because it's got two terms inside, and the second part is really just the extension of the first part, what the first part's going to turn into in the next term. So if we write out a few terms of the series, I get 1 over 1 minus 1 over 2. And I'm not trying to simplify this along the way. If you go ahead and calculate 1 minus a half equals a half, you'll kind of lose the idea here that this whole thing collapses back down. Now if we plug in n equals 2, I get a half minus a third. If we plug in n equals 3, I get a third minus a fourth. And this just goes on forever. So those halves cancel because I've got one positive, one negative. Those thirds cancel because I have one positive, one negative. And really all we're left with is our very first term. And then we'll end up with a subtraction of the limit as n approaches infinity for 1 over n plus 1, which is the second piece. So in this fraction, as you plug larger and larger and larger values in for the n, our denominator keeps getting larger and larger and larger, and the overall value of the fraction gets smaller and smaller and goes to 0. So this limit here equals 0. That means our series converges to 1. but not all telescoping series are convergent. Let's say we've got n minus n plus 1. The second term in this series looks very similar to the first. It's just what we would get when we plug the next value of n in. So if we write out a few terms here, we get 1 minus 2. Plug in n equals 2, you get 2 minus 3. Plug in n equals 3, you get 3 minus 4. And this just continues forever. We see that this is going to just collapse down to be your very first piece minus the limit of your second piece. And as n approaches infinity, n plus 1 is also going to approach infinity. So what we have here is 1 minus infinity, which is going to be a really huge negative number, and we can't specify what exactly that number is going to be. So this is divergent.